Hi everybody. Today we're going to talk about long division, something you guys have done for a long time, although you may not have done it in a long time. And we're going to hope to apply it not just to numbers, but to polynomials. And so the idea is that we're going to start by doing a long division problem with numbers. And then we're going to see how we can adapt those same techniques in order to carry out long division for polynomials. So let's go ahead and get to it. We're going to start with this numerical example, 3,571 divided by 11. Okay. So depending on where you grew up, you might write this in slightly different ways. It will help you here to learn the method and the format that we do here. However, if you have other strategies, they may indeed work and should yield the same result. But I'll be teaching the American method. So this is, let me see, we set up our long division box. The number that we are dividing into, 3571, goes underneath. And then the 11, the number we're dividing by, goes out in front. We also have names for these. This is called the divisor, the thing on the bottom, and this is called the dividend, the thing that we're dividing into. Okay, so here's how we do this American system long division. We do 11 into 35. We only take as many of these digits as we need to get bigger than 11. 3 by itself doesn't work, so we do 35. 11 goes into 35, and I know that 11 goes in 3 times. If I do 4 times 11, it gets too big. It becomes 40-something. It passes 35. So it goes in 3 times. Now, we do the 3, we multiply it by the 11 and put the result underneath. So this 3 times 11 is 33. Next step, this is important. We put a subtraction in the front of that 33. That is, we multiply that 33 by a negative 1. And then we subtract 35 minus 33. 35 minus 33 gets us a remainder of 2. Now, we look to the right. If there are more digits here, we bring the next one down. In fact, we bring down as many as we need in order to make a number here bigger than 11. It turns out that if we bring that 7 down, we will get the number 27, and that is bigger than 11. So we only need to bring down just that one. Okay, down. Cool. Now we do the process again, like so. Instead of 11 into 35, we now do 11 goes into 27. How many times does it go in without going over? It goes in, it looks like twice, because 2 times 11 is 22. So I'm going to put a 2 up here. That's how many times it goes in. I do 2 times 11 and put the result under, so that gets me 22. And then I multiply by negative 1. And finally, I subtract 7 minus 2, that's a 5, and the 2 minus 2 is a 0, so we get a 5 down below. All right, now we do it, same process. We bring the 1 down, and now we have the number 51 to work with. So we say 11 goes into 51. We're now thinking of this 11 into this, and it goes in how many times without going over? It goes in 4 times. So in this case, 11s are not too difficult to work with mentally, but you might have to do a little work on the side to figure out how many times it goes in. Put the 4 on top. 4 times 11 is 44. And then we subtract. We'll put that minus in there. 51 minus 44 is a total of 7. Looking up above, there's no more digits to work with here. We've reached, this is the ones place. If we wanted to continue getting a decimal answer, then we could put a dot and a 0 and bring that 0 down and continue this process. We would put our decimal point there. But we are just interested in division and remainder. So we have now said that 11, it goes into 3,571. It goes in 324 times, and there's a remainder of 7. And just as an observation, we sort of write this in a couple of different ways. One way that we write it is we can write 3571 over 11 is equal to 324, and then the remainder 7 is plus 7 elevenths. Yeah. So this is sort of one way of expressing what we've just done. We've taken the fraction and rewritten it as a whole number, plus what we call a proper fraction, a fraction where the top is less than the bottom. There's another way to express this, which is instead of thinking of this division as a way of rewriting this fraction, we can think of the division as a way of rewriting just that number that's on the top, the 3571. So this is another way of saying this is that when we divide 3571 by 11, we get that 3571 is equal to 324 times 11. That's how many 11s, plus another 7. And you'll notice that whether it's in this form where we rewrote the entire fraction, or whether it's in this form where we just rewrote the top number, you sort of get all the key numbers in there. You have the dividend and divisor, the dividend and the divisor. You have the number of times it went in, 324 times. We call that the quotient. And then we have that plus 7, that's the remainder. Okay, so we're going to kind of use this as our model. And we're now going to attempt to do the same thing where we're dealing with polynomials instead of with numbers. Let's go ahead and do it. So, once again, we set up our division sign here. I'll maybe make that a little longer. Here we go. And the number on top, the dividend goes inside. So that's our x cubed plus 5x squared plus 4x plus 2. And we're dividing by this term on the bottom, by the polynomial on the bottom, x plus 3. So this is x plus 3 into x cubed plus 5x squared plus 4x plus 2. Now, just a couple observations. As we do this process over here, you're going to find many similarities with the process over here. But of course, we're dealing now with polynomials instead of with numbers. And so you're going to see some differences also. And so I want you to be alert to the places where things are the same and the places where things are different. I'll try to describe what kind of the analogous thing is between these two sides. They both have a dividend, that's the guy underneath. And they have a divisor, that's the thing in the front. In this case, it was 11. In this case, it's x plus 3. But sort of structurally, when you think about this written down here, it's very important when you're doing division of numbers that you deal with the digits, the individual digits, and sometimes combine them together, look at 2 digits in a row or 3 digits in a row. But the digits are kind of the main thing here. Whereas over here, it's not the individual digits that you see in the numbers, it's the terms. Each term is the number and power of x. So this is x cubed, that's a term. This is 5x squared, that's a term. This is 4x as a term, and this is 2 as a term. So somehow, when we look over here, we're kind of thinking analogous with these terms sort of play the role of our digits. All right, let's go ahead and do it. The way that we begin is we look here, and in fact, it's simpler than in the case of numbers because we only care about the first term out here, the x, and we want to know how many times does it go into x cubed. And the right way to think about it is the following. What do you have to multiply this by to get x cubed? And the answer is you multiply x by x squared. That's what gets you x cubed, because x squared times x, when you multiply, you add the exponents, and then you get your x cubed. Okay, so this is the number that goes on top. And the way that we carry it out from here is we multiply this x squared times this entire thing and put the result down here. So that's really important. When we were figuring out what to put here, we only considered the first term and the first term. But when we multiply by the entire thing and put it down below. So x squared times x plus 3, we do x squared times x, that's x cubed. And x squared times 3 is 3x squared. Okay. So we've multiplied and written underneath. Now, very important, we now take the entire bottom and we make it negative, like so. We multiply by -1. This is just like when we made the number negative down here. The only difference here is that if you think of this in parentheses, that negative is going to distribute, so that negative will be in front of the x cubed, but it will also make that 3x squared become a negative. Okay. Now, let me just change colors so that we can keep track of what we're doing. I'm going to distribute that negative through. So I'm going to cross it out there. I'm going to make it negative here, cross out that plus, and make it negative there. The idea here is that we want to remember that that's negative and that's negative. And I've sort of gotten rid of my parentheses by doing that as I distributed that negative through there. To get rid of that parentheses too. Okay. Okay, and now we add. So we have x cubed minus an x cubed gives us 0 down below here. So we have 0. And we have 5x squared minus 3x squared gives us 2x squared. Great. Next step. Well, we look to the right and we bring the next term down. Let's go ahead and do it. So this is plus 4x. And now what we're going to do is repeat those same set of steps, but instead of looking at x plus 3 into here, we now look at x plus 3 into here. And remember, the first step is we look at the first term here, the x, and think how many times does it go into 2x squared? Or another way to say that is, what do we have to multiply x by in order to get 2x squared? And a little thought should give you that we have to multiply it by 2x. You can mentally check this by just going 2x times x. The x times the x gives you x squared, and that 2 in the front, so that gives us 2x squared. So when we figure out what number to put on top, we only look at the first term here and the first term here. Next step, we take that number, we multiply it by this entire thing, both terms, and we put the result underneath. So 2x times x is 2x squared. 2x times 3 is plus 6x. Well, now that step is done. And then next step, we make the whole thing negative. That is, we multiply by -1. Now, once again, I'm going to go ahead and distribute that negative through. So I get rid of that. I make that a negative 2x squared, make that a negative 6x, and get rid of that guy. All right, what's our next step? Well, we add or subtract straight down here. So 2x squared minus 2x squared is 0. 4x minus 6x is negative 2x. And I guess I put a plus there, but I didn't need it. It really should be minus 2x. Good. That step is done. So now we bring this, we look up to the top, and we bring the next term down, plus 2. Now, let's continue. We're now going to repeat the process again, starting with x plus 3 and going into this minus 2x plus 2. The x, the first term, we're going to go into the first term here, negative 2x. X goes into negative 2x how many times? Or another way to say that is, what do you have to multiply x by to get negative 2x? And the answer is just negative 2. You mentally check by saying negative 2 times x gives you negative 2x, so that's a good check. We're now going to do the next step, which is to multiply this by both of those terms at the front and put it down below. So that negative 2 times x is negative 2x. Negative 2 times 3 is minus 6. And then finally, don't forget, we have to make that negative. That is, we have to multiply by -1. Now, just be a little careful when simplifying this. If we distribute the negative through, that negative is going to disappear, but it's going to combine with that negative to make that a plus. And it's also going to combine with this negative to make that a plus. So those both become positive in the bottom. And you can see that what we're really doing on this step is we're not making everything negative, we're just multiplying by -1. And then whether we end up with negatives or positives depends on whether things were positive or negative in here to begin with. Okay, so let's go ahead and subtract or add. That's our next step. We have minus 2x plus 2x, and those cancel out. They give us 0. And then Plus 2 and plus 6 gives us plus 8. You'll notice here that this 8 has a smaller degree than the thing we're dividing by, but then the divisor. The divisor has a degree of 1 because it has x to the 1 power. This has a degree of 0 because it doesn't have an x in it. And once the degree of this is less than the degree of your divisor, then you stop, and this gives you the remainder. So, just to label everything appropriately, let's see, this is the remainder here is 8, and the remainder on that side was 7. And what I want to do is just use this same idea. So we're done with this problem. I just want to use this same idea to rewrite, to express the result in two different ways. One is we can take the original fraction. It looked like this: x cubed plus 5x squared plus 4x plus 2 divided by x plus 3. That's a fraction. What is that equal to? Well, it went in this many times with this remainder. And so the way that we do it, just following the way we did it for numbers, is it goes in x squared plus 2x minus 2 times, and then plus, for the remainder, we just do it over x plus 3. It's the remainder 8 over x plus 3. So this is a way of rewriting this fraction. And the pieces go in the same place. That is, we have the dividend and divisor, we have the quotient, and then we have the remainder over the divisor. And that just matches what is going on here. And we can do it similarly here. Another way to think of this is a way of rewriting this guy on the top, that polynomial on the top. This work that we've done shows that x cubed plus 5x squared plus 4x plus 2 is equal to x squared plus 2x minus 2 times x plus 3, and then plus that remainder of 8. So if you were to carry out this long division and give me either this or this as a final statement of your work, I would accept either one. Which one do we use in practice? It depends on what our goals are. Sometimes we're working with a fraction that we want to rewrite, and sometimes we're doing something like trying to rewrite a polynomial by factoring something out of it. This doesn't quite factor out. It has that plus 8 hanging out over there, but so be it. Okay, that's it. In our next video, we're going to look at some of the applications of this idea.